Okay, let's start by considering a function. And we suppose that this is the value a, and this is the value f of a. This is the function y equal to f of x. And then at this point, f of a, we can't compute the equation of the tangent line. Just denote this as t1 of x. This is a line, and this line is equal to f of a plus f prime of a times x minus a. Notice that it is a line, and evaluated that a is f of a, then this line goes through this point, and the slope of this line, which is the coefficient of x, is f prime of a. Then this is effectively the equation of the tangent line. Then what we're going to do in this video is we're going to estimate the error of this line with respect to the function f. That, what I mean is, given a b, we can compute f of b using the function, and we can compute this value, which is t1 of b. Then the problem is how to estimate that error. That error is just f of b minus t1 of b. This is the error, and we want to estimate that. And what we're going to show is that this error is equal to the second derivative of the function at some particular value x star over 2 times b minus a squared. This is good because that says that if b is close to a, then b minus a is small, b minus a is even smaller, and is multiplied by this number. That x star is a value that is between a and b, and then this is something good to have an error in this form. But then we're going to just denote this error as c over 2 times b minus a, and we're going to show that that c is equal to f2 prime of x star. Then this is what we want to show. And then in order to prove that, we forget about this part, and we just call c equal to f of b minus t1 of b times 2 over b minus a squared. That's just the error. This is the error, and we write it like this. And we want to show that this error is the second derivative at some point x star. How to prove that? In order to prove that, we define this function g of x equal to f of x minus t1 of x minus c over 2 times x minus a squared. Then we know that by definition of c, we know that g of b is 0. G of b is f of b minus t of b minus this. We know that this is equal to 0. And on the other hand, we also know that g of a is also 0. And actually, since this is like the first order approximation, it's easy to check that g prime of a is equal to 0. Something that we're going to use in this proof is the following fact, that if we have a function, any function defined on an interval, let's say if you have an interval a1, b1, and you have a function that is 0 here and 0 there, and it's continuous and it has a derivative, then at some point in between, the derivative is equal to 0. We're going to use that. That's the Rolle's theorem, and we're going to use it. And then, since we have that this function satisfies that g of b is equal to 0 and g of a equals 0, then we know that there exists x1 between A and B such that g prime of x1 is equal to 0. Then this function, let's try to make this bigger. Here we have A, here we have B. We know that at this point g of A is 0 and g prime of A is 0. But since g of A is 0 and g of B is 0 by the definition of C, then there is a point x1 in between such that here at this point we also have that g prime of x1 is equal to 0. But now, since g prime of A is 0 and g prime of x1 is 0, then we can find a point x star between A and x1 such that the derivative of this function, but the derivative of g prime is g double prime of x star is equal to 0. But let's write this condition. We have that g of x is equal to f of x minus f of A minus f prime of A times x minus A minus c over 2 times x minus A squared. Then g prime of x is just f prime of x minus f prime of A minus c times x minus A. As I pointed out before, g prime of A is 0 as well. But then let's compute the second derivative. The second derivative of x will be f, the second derivative of f minus c. But then if we evaluate at this special point, we get that g double prime of that special x start is 0. But that means that the second derivative at x star must be equal to c, and this is what we wanted to prove. Then we have shown that the error, which is f of x minus f of A plus f prime of A times x minus A, when you replace x with b, this error can be written as the second derivative at some special point x between A and B over 2 times x minus A squared. We can extend this argument and prove the error in general. The Taylor polynomial of order n, by definition, is just f of A plus f prime of A times x minus A plus the second derivative at A over 2 times x minus A squared plus the nth derivative at A over n factorial times x minus A to the n. And essentially, this is the best polynomial of order n that fits the function at x equal A. Then if this is A and this is f of A, then Taylor polynomial of order 1 is the best polynomial of order 1 that fits the function. This will be the best polynomial of order n that fits the function near the point A, f of A. And actually, the reason we have these coefficients is because we want this property to hold true. We want f of A to be equal to Tn of A, we want f prime of a to be Tn prime of a, and we want the nth derivative at a to be equal to the nth derivative of the polynomial at a. Then we have all these properties, and then we can show that the error, which is f of x minus Tn of x, when we replace x with b, that this error is equal to the nth plus 1 derivative as some special x over n plus 1 factorial times x minus, times b minus a to the n plus 1. You can show that that's the error. And the proof is exactly the same. We define c such that this error, we know that we have these two functions, we can compute the difference, and then we can solve for c and find the c that satisfies that c over n plus 1 factorial times x minus a to the n plus 1 is equal to the error. And then we need to show that the c is equal to the n plus 1 derivative as some special x, where this x is between a and b. We do the same argument. We defined g of x equal to f of x minus the polynomial evaluated at x minus c over n plus 1 factorial times x minus a to the power of n plus 1. We define this function. It's very easy to check that this function evaluated at a, because of all these properties, it's very easy to check that g of a is 0, g prime of a is 0, and the nth derivative at a is also 0. Right? These properties implies that. And also, by the definition of c, we know that g of b is equal to 0. And now we are ready to just do the same argument. We have that here is a, here is b, and since this property holds true, then at some point x1 between these two, we know that g prime of x1 must be equal to 0. But now, since I know that g prime of a is 0 and g prime of x1 is 0, then I know that at some point x2 in between here, the derivative of this function, the derivative of g prime of x satisfies that at a is 0 and at x1 is 0, then at some point this derivative is equal to the derivative of this derivative, which is the second derivative. At that point is equal to 0, but we also have that the second derivative at a equals 0. Then if we continue with this argument, we will end up with this, that the nth derivative at a is equal to 0, and the nth derivative at some point x to n is also 0. Here is, continue with this argument, you get an x to n, and at this point the nth derivative of a, g at a is 0, and the nth derivative of g at this point xn is equal to 0. But then we know that at some point the n plus 1 derivative at some special x star, that this is equal to 0. But now we can compute this derivative. We know that the n plus 1 derivative of t is 0, then we can easily compute that the n plus 1 derivative of x is just the n plus 1 derivative of x. The n plus 1 derivative of this polynomial, this is a polynomial of order n, is 0. And we can easily check that the n plus 1 derivative of this expression, when you take the first derivative, is n plus 1 cancel and n plus 1, and you get just n factorial. You keep doing, this is just c. And then this condition just implies that the n plus 1 derivative at this special point minus c is equal 0, and this is what I wanted to show. Then in general, the error when you approximate using a polynomial of order n is given by this expression. Okay, this is it for this video.